Hi, welcome back to a new lecture from Transformers for Vision. In this lecture, we'll be doing a very specific thing, which is hand calculating how exactly did GPT-3 get 175 billion parameters. This exercise will give us a fairly good intuition about the architecture of the LLM itself. And we will also have a fairly good idea how these parameters are distributed inside that architecture. How many are there in the input part of the neural network, how many are there in the transformer layer, and how many are there in the output part. If you don't know the architecture of a large language model, I highly recommend you to go through at least one video that explains the architecture in detail, because here I will not be going into all the details of the transformer architecture because that will make the lecture very long. Instead, I will assume that you have some basic knowledge about the large language model architecture, you have some basic knowledge about the transformer block, etc. And then from there, I will walk you through step by step on how exactly to calculate these parameters. And don't worry if you have forgotten how exactly the architecture of an LLM looks like. I will give you a brief recap so that you can refresh. Now, you might be wondering, how is GPT-3 architecture relevant for vision-based tasks? The reason why I am explaining this to you is so that you can carry forward the same intuition that you get from this lecture also to the cases where you talk about or you learn about vision transformers. So that's the reason why I introduced this lecture. So let's first look at the architecture of the LLM itself. So this is the overall rough architecture. Don't worry by seeing multiple blocks. I will divide it into meaningful chunks. So the first block, so here you can see 1, 2, 3. We can look at the entire LLM architecture in 3 blocks. First block is the part that deals with input. So you give an input or a prompt, and some things happen to this input where it is tokenized, and a position embedding is also done. So I will explain what these means, but just keep it in your mind. Then you have transformer block, where you have 2 layer normalizations, these 2 blue blocks. You have dropout happening at 2 locations. You have a feed forward neural network, and you have the main guy, which is the multi-head attention. So this transformer block will be repeating 96 times in series in the GPT-3 architecture. That is one thing. This is one place where you will hear the number 96. Another place where you will hear the number 96 is in the number of heads inside this multi-head attention, which is 96 heads in parallel. So these two 96 are 2 different numbers, so please don't confuse between them. Then the last block is the output block, where the final prediction of the next word happens in the large language model, which has a normalization layer and an output layer. Now, what we want to calculate is how are these 175 billion parameters distributed in these blocks individually and also into these individual modules. How many billion parameters are there in each of these? Let's try to calculate. So we will start very systematically. Let us look at the input part. A GPT-3 with 175 billion architecture models, 175 billion parameters have the following architecture. It has 96 layers. What does this mean? It has 96 transformer blocks in series. The token, which could be a word, which could be a subword, are represented using vectors of 12,288 dimensions. So each token is represented by a vector of these many dimensions. And within each transformer layer, you have a bunch of things. And one of the most important things is the multi-head attention. So each multi-head attention has 96 heads. So 96 heads make up one multi-head attention inside one transformer block. And inside these multi-head attentions, each of them take care of 1/96th of the dimension of your input token, which means 12,288 divided by 96 equal to 128. So the tokens are represented not in a 12,288 dimensional space inside these attention heads, but rather it is represented in a 128 dimensional space inside the attention heads, individual attention heads. And then they are concatenated back to create the 12,288 dimensional token back. Similarly, you have a feed-forward neural network over here. This one, this feed-forward neural network, what it does is it projects the token, the transform token of 12,288 dimensions into a space with 4 times more size. So whatever is the input dimension, in this case, it's 12,288. You multiply that by 4. So you are projecting it back, projecting it into that dimensional space, and then you project it back. So that is what is happening in the feed-forward neural network. I will explain the exact number of parameters when we calculate it. I'm not talking about the parameters yet. I'm just giving you the architecture related numbers, and then we can calculate the parameters later. Then you have a dictionary with a vocabulary size of 50,257, which means that many unique tokens exist in your vocabulary. And each token is represented by a 12,288 dimensional vector, please note. And context length, the number of tokens which you can feed to the GPT-3 architecture is 20,048. Sorry, 2048, my bad. So this is the general GPT-3 175 billion architecture. Now, based on this information, let's try to calculate the number of parameters. And finally, all of that should add up to 175 billion. Let's start with the vocabulary. So as I mentioned, the input token is a vector of 12,288 dimensions. So this is dimension 1, dimension 2, etc. up to 12,288. So this is the input token. I mean, this is one token. The vocabulary consists of 50,257 such tokens. And there are numbers inside each of these, right? Each of these are numbers that are trained so that you can have a good representation of each tokens. So let's say one word is a token, then the word cat, maybe this is the token corresponding to the word cat. This is the token corresponding to the word, let's say zebra. There are subwords also. I'm just simplifying it here. So how many parameters are there in this vocabulary? You will have 50,257 multiplied by 12288. Those many parameters will be there. And what is this number? Let's calculate using calculator. 50,257 multiplied by 12288. This is 617.55 million. So this will be 617.55 million. So these many parameters are there in our input embeddings because the vocabulary size is this much. Now, how many tokens are there in our context window? Our context window size, as I mentioned, is not the entire vocabulary. It's only 2048 tokens. And each token, of course, it is 12,288 dimensional vector, which means the total number of parameters, trainable parameters, to construct a position embedding, because what you would be doing is you won't be taking the token value directly and using it. You take the token value from the dictionary, yes, but on top of it, you add a position embedding. Why is position embedding important? Let's say the dog chased another dog. So here the dog word or token is appearing twice, but this is appearing in the position number 2 and this is appearing in the position number 5. So there should be some difference in the way this dog is represented and this is represented, and that's why you have to add some information about the position to your input embedding. And how many such position embedding vectors do you need? You will need as many as there are number of tokens in your context window. So context window is 2048. So you will need that many position embedding vectors. So what would this be? The number of parameters, 12288 multiplied by 2048. And this is equal to, okay, before we use calculator, let's roughly calculate how much this should be. So 2048 tokens in the context window, but roughly 50,000 tokens in the vocabulary, which means you have 1 by 25th number of tokens in your context window. And what would that mean? The number of parameters will be 1 by 25th of this, which should be roughly 25 million, right? 25 multiplied by 25 is 625. So roughly we should have 25 million parameters here. So this number, let's calculate exactly to see what it is. So 12288 times 2048 equal to 251,65824. So this is 25.1 or 25.2 million if I round off to only one decimal point, these many parameters. So in the embedding part, in the input embedding part, totally how many parameters do we have? Due to vocabulary, you have 617.55 million. And due to position embedding, you have 25.2 million. So if you add these two, roughly this should come to 17 plus 25 is 42. So this should be 642.75 million, roughly. Roughly these many parameters should be there where in our part 1 of the transformer architecture, which is part 1. Part 1 is this 642.7 million parameters in this part. And compare this to 175 billion. This is 0.64 billion, right? So it's very small compared to our total number of parameters that we are expecting. Now let's go to the second part, which is the transformer block itself. As I mentioned, there are 96 such blocks. I'm just drawing one block here. And there are few places where parameters can be expected. There will be some parameters in each of these layer normalization. There will be, of course, some parameters in the multi-head attention. Dropout does not introduce parameters because you are simply randomly not using certain neurons. So it won't introduce additional parameters. But there will be additional parameters in the feed-forward neural network. And this will repeat 96 times. So if we do the calculation for one transformer block, whatever numbers we get, we simply multiply it by 96 to get the final total number of parameters due to the transformer blocks. And later we can calculate the output block, the number of parameters in the output block separately, right? So now, what should we look at first? Let's look at multi-head attention. So in multi-head attention, what's happening is the following. We have the embedding. So this is the vector in which position embedding is added. So the dimension is still 12288. And what happens is we pass this to each of the 96 attention heads in the multi-head attention. So this 96 is different, right? This 96 is within an individual transformer layer. And what would be the dimension of this token inside those attention heads? It will be 1 by 96th of 12288. 12288. 1 by 96th of 12288 is 128. So the dimensionality of our token inside this individual heads of the multi-head attention is 128. So how do you transform something with 12288 dimensions to something with just 128 dimension? Here you have the query vector, key vector, and value vector. And to perform this transformation, you will have bunch of weights for query, bunch of weights for key, and bunch of weights for value. So let's calculate that. So number of weights for key will be weights for, let's say, or rather query will be 12288 multiplied by 128. But there could be bias also, which you can add here. So bias is added at the nodes at the output. So how many such bias parameters can you add? Because you have 128 as the dimension here, you can have 128 bias values. So this plus 128. So this will be biases in the queue plus weights. And same thing repeats for key. So key also is exactly the same. You have 12288 times 128 plus 128. This is the bias. And value is also the same. 12288 times 128 plus 128. And what would this number be? So let's calculate 12288 times 128 is equal to something. Then you add 128 to this, doesn't change much. Then you multiply this by 3 because I have key, query, and value. So this will be 4.72 million, right? So this number turns out to be 4.72 million. Let me just draw it. 4.72 million. Where is this 4.72 million coming? It is coming in one of these attention heads, or 4.718 million. That was the number that we got. Like this, there are 96 attention heads in one transformer layer. So total number of parameters here would be 96 multiplied by 4.72 million. So let's do that. So this multiplied by 96 equal to 453 million. So the total number of trainable parameters inside these this whole attention, multi-head attention, is what? 453 million. 453 million. Okay. So let's just write it down. Let's go back to our figure and just write down that multi-head attention. Yeah, one more thing is there. Before we add this 453 million, we have one more transformation. So what happens is you get 1 by 96th of the dimension from each attention head, and then you concatenate each of those outputs to get back the 12,288 dimensional transformed input token. But then you perform one more transformation of this final concatenated token through an output matrix. Output meaning just the output from the multi-head attention, not the final output of the LLM. So here dimensionality does not change. Dimensionality will remain to be 12288. So which means the transformation that you are doing is through a matrix of dimension one of number of parameters 12288 multiplied by 12288. You can imagine it to be like a simple neural network with fully connected connections. But then there could be bias parameters that is added at the nodes in the output. So there are 12288 number of nodes. So you can add that also here. So this plus 12288, and this will be 12288 times 12288. This is equal to something. Then that plus 12288 equal to 151 million parameters. So this is equal to 151 million parameters, where in this output transformation matrix. So you have to add this 151 million to 453 million. So 151 plus 453 equal to 604 million. So finally, inside our multi-head attention, we will have multi-head attention plus counting the output transformation, we will have 604 million parameters. So we can note this down over here, 604 million parameters. We are still far, like a long distance. Oh, I'm sorry. This, let me just make sure that, yeah, it's correct. 604 million. Yeah. We are still far away from the 175 billion, but we will soon get there. Now let's look at the layer normalization. Both of them are identical. So we just need to do calculation for one of them, and that same number will apply. The number of tokens will be the same for both. So in layer normalization, what happens is you have input token. I mean, after transformation, it still retains this dimensionality. What you do is there are individual values inside each of these dimensions. They are normalized by subtracting the mean of all these values and dividing by the standard deviation of all these values. So you want mean to be close to 0. I mean, the mean of the distribution to be close to 0, standard deviation of the distribution to be close to 1. And then each of those are scaled by a scaling factor, and you add a little bit of bias to each of these numbers separately. So the total number of trainable parameters are how many ever number of betas and how many ever number of gammas are there. So the number of betas will be equal to number of dimensions of this, which is 12288. Number of gamma parameters will also be the same, which means the total number of trainable parameters in each layer normalization is 12288 times 2, which will be 12288 times 2 equal to 24576. In millions, we can express this as 0.024 million. That many parameters in each of these layer normalization. So let's go back and draw. So this will have 0.024 million. This will also have 0.024 million. Okay. So these three are done. Now what else? Now we have feed forward neural network. So what feed forward neural network does is its input dimension is again the transform token, which is of 12288 dimension. Its output is same. So this feed forward neural network does not change the final dimensionality, but what it does is it projects this incoming vector into a higher dimensional space of 4x the number of dimensions, and then it projects it back. So here there is a transformation happening from this dimension to 4x whatever this number is, and that would require certain number of weights. The number of weights will be 12288 times 4 times 12288. So this will be the number of weights, but you can have bias also for each of these. So the total number of bias parameters will be this number. So this plus 4 times 12288. So let's calculate this what it is. 12288 times 4 times 12288. This is equal to some number plus 4 times 12288. I think I might have messed up the brackets. Let me do this once more. Okay, 12288 times 4 times 12288 equal to, so this is 603.97 million. So this will be 603.97 million plus whatever is 4 times 12288 equal to 90. So this is 0.909 million, right? 0.909 million. So this will be around 604 plus 1, roughly 605 million parameters, something like that. 909, 604 plus 0.9. So like something like 604.9 million, something like this. So this is the first transformation from here to this. Now from here to here, you are going back in dimensionality. So what will this be? Total number of weights will be 4 times 12288 times 122. So this 4x I have written is 4x of whatever this is. That's the number of dimensions here. And here it is 12288. So that many, so your matrix that performs this transformation will have these many parameters. And then you can add bias also at the output nodes. So number of nodes equal to 12288. So you simply, that many bias parameters will be there. So what would this be? This will be 4 times 12288 times 12288 equal to something, that plus 12288 equal to 603.99, which is 604 million. So this will also be 604 million. So the sum total of this entire feed forward neural network will be 604.9 plus 604 million, which is 1208.9 million, which we can approximate to be 1209 million. Sorry, 1209 million. And in billion, what will this be? 1.209 billion, which is 1.21 billion roughly. So 1.21 billion parameters in this feed forward neural network. See, very this is probably the biggest out of all. Now, what are the total number of parameters in one transformer block? It will be 1.21 billion plus 0.02. So this we can ignore because in billion, this will be even smaller. This is 0.024 million. So this layer normalization can be ignored to perform our approximate calculation. So you have 1.21 billion plus 604 million is 0.604 billion, which we can say 0.6, which is 1.81 billion parameters in one transformer block. 81 billion parameters. But like this, there are 96 transformer blocks in series. How will it look like? So all these things inside this gray box will repeat 96 times like over here. So transformer block 1, transformer block 2, block 3. I mean, I'm calling it as layer 1 like this 96. So your total number of parameters due to the transformer blocks will be 1.81 billion multiplied by 96. So this times 96 equal to 173.76 billion. So this will, like this, if you multiply by 96, 173.76 billion. So now look at the distribution. Out of the 175 billion, we got almost 174 billion. And we understand that most of them are coming from the transformer block. Just 0.64 billion is coming from the input part. Now let's see how much is coming from the output. So the dimension of the token which has been transformed is still 12288 by the time it reaches this layer normalization. And what would that mean? It would mean the same thing. So earlier in the layer normalization, what did we do? We calculated the mean and standard deviation of this. We subtracted the mean so that the mean of the distribution becomes 0 and standard deviation becomes 1. So we did that. And then we multiplied with a scaling factor, which is a learnable parameter. We added a bias parameter, which is also learnable. So we will have what? 12288 number of beta parameters, 12288 number of gamma parameters. So total will be 12288 multiplied by 2, again 0.024 million parameters in the final feed forward layer. Where is that? This one. Sorry, final layer normalization. So this will be 0.024 million. Now what happens in the output layer? Our dimensionality of the token is still, the transform token is still 12288. Now at the output, we want something where we can say, hey, my vocabulary looks something like this. I have 50,257 tokens and I want to predict the next word or next token. So basically I want to know out of these 50,257 tokens, which one comes as the next token based on the current prompt input. So it'll be nice to have a distribution which looks like this, where I have bunch of values of total number 50,257, and maybe one value out of this is predominantly bigger. So let's say the ID of this is 2027. This ID, the 2027th token, let's say that is cat. Let's say that is this token, which means the next word which I'm supposed to predict, or the next token that I'm supposed to predict, is highly likely cat. I mean, there will be a probability distribution. So the value associated this might be 0.8. Maybe the rest of the values add up to 0.2. So that 0.8 and remaining values will add up to 1. So it's like a probability distribution. It goes through softmax operation to have these numbers. But did you notice the input token? I mean, the token after transformation was 12288, but now it has to somehow become 50,257. Like what? Like something like this. So this 12288 has to somehow transform to this, which means another matrix ideally would be needed of dimension what? Of dimension of number of parameters 12288 multiplied by 50,257. Plus you can have bias at the output. So you can add another 50,257. But in GPT-3, so how many parameters would this have added? This would have added an additional 12288 times 50 to 57. That will be 617 million plus 50 to 57, still 617.6 million. So we would have gotten around 617.6 million extra parameters. But in GPT-3, they don't do this, because you already have a matrix of these many parameters, which you had over here. Because your vocabulary had these many tokens and each token was 12288. So you had, if you remember, you had already bunch of parameters which took care of the vocabulary part and individual token part. So what is done in GPT-3 is these same weights are used. So you don't create new trainable weights at the output. Instead, you use the same thing which you used at the embedding. So you don't have these numbers. So this does not exist in GPT-3. So this number is 0, but you will have bias 50,257 parameters as bias, which is 0.05 million. So the total number of parameters in this is 0.05 million. So that's it. That's all the number of parameters. So your total number of parameters will now be 173.76 billion plus 0.64 billion plus these are small, like this is ignored because it's so small compared to these numbers. So this will be what? 173.76 plus 0.64. 173 point, sorry, 173.76 plus 0.64 equal to 174.4, which is approximated and said to be 175 billion parameters. So this is how you get the 175 billion parameters in GPT-3. And just notice the distribution. 1.81 billion parameters are coming in individual transformer blocks. Within that, one third of the tokens are coming in, one third of the parameters are coming in multi-head attention part. 2/3 are coming in the feed-forward neural network. And like that, you have 96 transformer blocks, which means 174 or around 174 billion parameters come in the transformer block itself, out of which 2/3 are attributed to the feed-forward neural network. So 2/3 of 174 billion, it will be roughly slightly less than 120 billion, right? Slightly less than 120 billion out of 175 billion are belonging to this simple feed-forward neural network. Amazing, right? And 0.6 billion is in the input part, and a very, very negligible amount, 0.075 million is in the output part. It could have been 617 something million if we were having the weight matrix in the output layer, but we use the same one from the embedding. So this is how you should understand the distribution of parameters are in the GPT-3 architecture. This knowledge also translates to other models. So now you have a better understanding of how the architecture is using the parameters. Where exactly is it coming? Unlike we might think, most of the parameters are not coming in multi-head attention. 1/3, yes, 1/3 are coming in multi-head attention, but 2/3 is coming in the feed-forward neural networks. Feed-forward neural network is much simpler. You are just projecting into a 4x dimensional space. You are projecting it back. It's a very simple part, but 2/3 parameters are coming there. Amazing, right? So I hope this brings a lot of clarity. All these learnings also translate to when you try to understand vision transformers, because there also all these parts of the architecture will come into picture. So I just wanted to present you with GPT-3 because it's very famous. The model architecture is very famous, but the learnings translate to concepts in computer vision using transformers. So I hope you enjoyed this lecture. I will see you again in the next one. Take care until then.